In this presentation, we will discuss our group project titled Experimental and Analytical Investigation of Structural Response of a Scooter Deck Subjected to a Rider's Loading. This study focuses on understanding how the scooter deck behaves structurally when subjected to different riders' weight using basic solid mechanics principle. The scooter deck is a critical structural component because it directly supports the rider's weight during usage. When a rider stands on the deck, bending occurs, similar to a simply supported beam. If this bending is excessive, it can cause discomfort, long-term fatigue, or even failure. Although the beam theory can be predict deflection and stress, real structures may behave differently due to support conditions and material limitations. Therefore, this study combines analytical and experimental approaches. The main objective of this study are to measure the deflection of the scooter deck under different riders' loads, calculate theoretical stress and deflection using beam theory, and compare both results. The scope of this project is limited to static loading on the scooter deck only. Other components such as wheels and handlebars are excluded. Aluminum 6061 T6 is assumed as the deck material. For future improvement, the deck geometry can be strengthened by increasing thickness and adding stiffness. Material replacements such as aluminum 7075 T6 or carbon fiber is also recommended. Further studies should include experimental validation, dynamic loading, and fatigue analysis.
First, we go to methodology. First section, methodology and structure modeling. In this project, we analyze the scooter deck using Euler-Bernoulli beam theory. We model the deck as a simply supported beam with the wheel acting as the support. To represent the rider, we applied a point load directly to the center by testing weight from 50 kg up to 100 kg. We calculate the maximum bending and deflection to ensure the deck is strong enough and stays stiff under pressure. Next, we go to geometry and material properties for my team projects. First, deck dimension length 0.8 meters span between wheel attachment, and second width 0.08 meter standing surface, and third thickness 0.007 meters for critical bending resistance. And material that scooter is aluminum alloy 6061 T6. First, modulus of elasticity is 69 GPa, and yield strength to 214 megapascal, and third, ultimate tensile strength is 290 megapascal, and density 2700 kilograms per meter cube. This model we use a scooter. We get the scooter at the library PTTA, and we use for my team projects. Next, the theoretical equation and analysis goal. In this project, we use 4 equations to calculate the deflection for scooter. First, moment of inertia. Second, bending moment. Third, bending stress. And last one, mid-span deflection.
Assalamualaikum. So, my name is Muhammad Taufik bin Azmi, and I'm going to present about theory and calculation. So, this is our free body diagram for scooter deck, and this one is for evaluate structural performance, statically loaded, bending moment, load interact. So, our goal is to withstand 100 kilogram load without any stress, without failure. So, our assumption is linear elastic material, basic support beam, arrangement, and rectangular cross section. Okay, so we continue to next. The first one is project overview and objective. The primary aim is to perform a cooperative structural performance evaluation between two common manufacturing materials. And then success is defined by the deck ability to support a standard 100 kilogram static load without reaching its material yield point or experiencing permanent deformation. Our key parameter is to analyze focus on four critical engineering metrics. The first one is bending moment, the second is moment of inertia, and then the bending stress, and lastly is maximum deflection. So the second one is technical assumption and setup. So the structural model, a basic support beam arrangement with a rectangular cross section, and then the deck is defined as 0.8 long with a thickness of 0.007. So we're going to continue for number 3 and 4. Number 3 is material comparison between aluminium and carbon fiber. So the stress factor for both material was subjected to a calculated bending stress of 300.31 megapascal based on the 100 kilogram load. And then for weight advantage for both is carbon fiber is roughly 40% lighter than aluminium with a density 1.06 gram versus 2.07 gram. And then we continue for number 4 is key finding and recommendation. Aluminium failure is aluminium 6061 T6 is deemed not suitable because the bending stress exceeds its yield strength and its deflection far exceeds the 32mm allowable limit. So design iteration, the final recommendation suggests that while carbon fiber is the better material, the deck geometry may need to be adjusted to further reduce bending or deflection.
Hi, my name is Yogendran, son of R. Ravindran. My metric number is CD240383. Today I will be explaining about the results. The following table summarizes all the important values obtained from the theoretical analysis of the deck of the scooter under static loading. The parameters include geometric sizes, calculated bending moment, stress, deflection, and metal strength. The data evidently illustrate the structural response of the deck when subjected to a 100 kg point load at the center. Safety is our top priority, and our analysis proves that the current 7mm aluminum design is structurally unsafe for a 100 kg rider because the stress exceeds yield limits and deflection is 20 times the allowable standard. This deck will likely suffer a catastrophic snap failure during a real-world use. To fix this, we propose a two-part remedial strategy. First, we must optimize the geometry by thickening the deck at least 10 mm and adding internal ribs to limit bending. Second, we recommend upgrading the material. For high-end decks, titanium or carbon fiber offer the best safety margins. For mid-range models, switching to aluminium 7075 T6 provides a cost-effective way to double the yield strength. Ultimately, only a complete redesign can guarantee the structural integrity and durability required for the rider's safety. Looking at our comparison, the current design faces a critical failure. The calculated bending stress of 300.31 megapascal exceeds the yield strength of our aluminium, which is aluminium 6061 T6 by 25%. This means that under a standard 100 kg load, the deck will suffer permanent, which is non-reversible deformation. To solve this, we recommend moving to a superior materials, which is aluminium 7075 T6. It's a great economical choice that nearly doubles our yield strength to 503 megapascal. For premium performance, titanium or carbon fiber offers a yield strength up to 1000 megapascal. Our final verdict is clear. The current metal is inappropriate for this design and must be upgraded to ensure safety.
In conclusion, the analysis shows that the current scooter deck design using aluminium 6061 T6 is not suitable for a rider's that is 100 kilogram weight. Both bending stress and deflection exceed acceptable limits, indicating failure in terms of strength and serviceability.
In this demonstration, we are applying three loads, which is 50 kg, 75 kg and 100 kg, which is lightweight and average and heavyweight riders, which is shown in our report.
Now we will demonstrate the effects of different riders' weights on this scooter deck. I myself weighted 50 kilograms, and so I will be standing at the center of the scooter deck and remain stationary. At this load level, the deck shows a small amount of deflection, which is expected for a lower applied load.
Next we go to the rider 75 kilogram. The rider 75 kilo at the same position as before, and we can observe deflection. We can noticeable the 75 kilogram the higher deflection and the higher the load.
At this highest load, the rider is standing under the same static condition. At this highest load, the deck is experiencing the largest visible deflection, which is represent the most critical in our study.
As a conclusion, these scooters behaves like a simply supported beam, which means it reacts. The deflection increases according to the increase of the rider's weight. And these observations have we conclude in our analytic results in our report. Thank you.